Okay, we'll start the poster flash session. I asked the first speaker to already come in, Dana. And as every speaker approaches the end of his talk, which is 3 minutes, I ask the next one in line to already get ready here. And we have the timer beeping at 3 minutes, so please keep your time. Okay? So the first speaker is Dana Krepet.
Hi, my name is Dana. I'm a PhD student at Oded's HODS group. Today my poster is on lithium adsorption on armchair graphene nanoribbons. Now we all know that graphene has very interesting physical characteristics and electronic properties, and it's our goal to exploit this in order to use graphene as for chemical sensing purposes. One of the ways to do this, graphene in itself is inert, is to use alkali metal atoms as anchoring sites for better chemisorption of weakly binding molecules. So what we did is a set of density functional theory analysis on 2-dimensional graphene and 1-dimensional armchair graphene nanoribbons. You can see the lithium adsorption, they're marked in magenta circles. And we took into account different width of the ribbons, different adsorption densities, and different spin states. Now, previous studies, they focused on 1 lithium atom per unit cell, which means they took into account only the duplet spin state. However, one of the surprising results of our research was that the singlet spin state, when you take into account the total energy, you can see that the singlet spin state is the true spin state of these systems, which is accompanied by a better binding energy and better charge transfer. And when you take into account the densities, you can see that as the density decreases, you can also see that the binding energy increases and there's better charge transfer. So what we also demonstrated in armchair graphene nanoribbons, we know that they have controllable band gaps. And we demonstrated the changes in electronic properties. And you can see that when you absorb the lithium atoms, all band gaps decrease. And you can see in the upper graphs, you can see the density of state analysis. You can actually see the decrease in the Hoko-Luko gaps, and you can also see the shift in Fermi energy, which increases the metallic nature of the systems. But when you take a look at the band gaps, you can see that there is they turn to they become metallic only for large enough densities, and one of the explanations is that you can see over there in the Luko that there is lithium bridges that can conduct, and this disappears for lower densities. So for more information, come and see my poster, and thank you.
Hello, everybody. My name is Daniel Schwartzman. I work with Gil Markovich. Our project deals with studying ferroelectric nanoparticles, especially barium titanate in this case. In our project, especially deals with the phase transition of these nanoparticles, and we developed a novel way to probe the size-dependent phase transition of these ferroelectric nanoparticles. Especially trying to understand whether this size-dependent phase transition effect is origins from the true size effects like ferromagnetics, or is something dependent on the surface of these nanoparticles. So especially we try to use the plasmon nanoparticles to probe the phase transition of the barium titanate ferroelectric nanoparticles, which are attached to it. As you can see, these are barium titanate cubes with the nanoparticles attached to it, and we can probe the phase transition with probing the plasmon absorption of these nanoparticles. If you are interested, then please come to my poster. I can explain you in more details. Thank you.
Hi, my name is Dana, and I work under the supervision of Professor Yossi Shacham. I am a master's student. My research concerns high-K dielectrics as gate insulators for nano-biosensing. EIS, electrolyte insulator semiconductor, EIS capacitors can actually sense biological interactions, and their operation is based on electrostatic coupling between charged biomolecules and the semiconductor. Now, why high-K dielectrics? So the main advantages are, first of all, gate leakage currents, significantly reduced compared to conventional gates, and also physically thicker dielectrics. Self-assembled monolayers serve as intermediate layers for further bioattachment and also protect the lower layers. All the above techniques were done to characterize the films and all showed the presence of self-assembled monolayer up to 10 angstroms. And actually the main conclusion, the last one, all the results show that atomic layer deposited self-assembled high-K dielectrics can serve as a base for silicon-based biosensors. Thank you.
Okay, hi, my name is Tal, and I'm a master's student under the supervision of Professor Yossi Shacham and Professor Amichai Freeman from Tel Aviv University. My work is done on whole cell biosensors. In this case, it's genetically engineered E. coli bacteria cells that can sense the presence of a model toxicant, nalidixic acid, and express the enzyme alkaline phosphatase that its amount can be measured electrochemically. The E. coli cells in this case are deposited on a conductive chip and form a biofilm structure that is a thick film of bacterial cells that attach to the surface and is resistant and stable under harsh conditions. The biofilm main disadvantage is low permeability, and we try to compensate on this disadvantage by the application of DC and AC electric fields, which are assumed to improve and increase the permeability of cell membrane and the whole structure, probably by porous formation. I will summarize and say that the biofilms have large potential serving as the biological component of whole cell biosensors, and our results demonstrate that the application of DC and AC electric fields may improve the electrochemical signal that is generated by the whole cell biosensor.
Good evening, everyone. My name is Naama. I work under the supervision of Yoram Dagan, and our group, in general, studies the interface between strontium titanate and lanthanum aluminate. And my work, in particular, I am studying the way mechanical stress influences this very interesting interface. What is so interesting about this interface is that while both materials are by themselves insulators, there is a layer in between them that was found a few years ago to be conducting. And there is research all over the world trying to understand what is going on there and what is really the origin of this conductance. So in my work, what I was measuring pretty much is the transport measurements, resistance and Hall measurements for under the influence of a magnetic field and also in varying temperatures. And so far we have very interesting results that show clearly that stress does matter. And well, I'm not going to discuss actually the details, but I strongly invite you to come to my poster, which is right next to the coffee machine, so it's very easy. First one, so welcome. Thank you.
Hi, I'm Reuven Boxman, and I'm a perpetual student. What we'll present in our poster is a method of producing nanoparticles using an electrical discharge. What we do is we have two electrodes in a liquid, in this case ethanol, and basically we make an electrical spark between these two electrodes, which are made of nickel. And what this does is it produces crystalline nanoparticles of a nickel carbide that has a carbon concentration which is 3 times the equilibrium saturation value, and it's surrounded by an amorphous coating of carbon. What's good about this is that these particles are pretty much immune to acidic attack, and at a room temperature, in other words, at all temperatures higher than about 8 to 9 degrees Kelvin, they are super paramagnetic. We feel that these could be used in all kinds of applications. For example, magnetic fluidics, where you'd like to have particles which are highly magnetic, but stable chemically. Thank you.
Hello, my name is Nimrod Bachar. I'm from the group of Guy Deutscher. I will briefly review our work on linear magnetoresistance of granular aluminum near the metal-to-insulator transition. Basically, granular aluminum is a superconductor. It forms from nanograins embedded in alumina or aluminum oxide material. By changing the doping level of the sample, we can get a metallic behavior or insulating behavior. We can see that on the normalized resistivity measurements. You can also see in the middle you have the optimally doped samples, which shows actually quite constant dependence. But if we take and zoom into the resistivity curve, we can see that it changes around a value of the room temperature resistance. Now, we took and measured the magnetoresistance at several temperature points, and we can see that the magnetoresistance shows a quite known behavior at low magnetic fields, and up to 10 Kelvin, it's known as ghost critical fields, suggested by Kapitunik and Deutscher. But on the other hand, and unexpectedly, we show, or we exhibit, the samples exhibit linear magnetoresistance, negative and linear magnetoresistance at high magnetic fields, and up to 50 Kelvin, as you can see at the lower graph. We can suggest that this behavior is a spin baramagnetism of a single grain. If we take a 2 nanometer grain, we can see that we have one spin with no excitation of other spins, and this spin, it can just tunnel between the grains, and this is actually, or basically, the transport mechanism of our sample. And you can ask me more questions when you can meet me at the poster session. Thank you.
Okay. Hi, everyone. My name is Roy. I'm a master's student at Shachar Richter's group. And my work involves designing and fabricating logic gates in a method that's different from what's currently available in industry, which is CMOS technology. We have a design that's called a go-to pair that is essentially a logic gate. Logic gates, for those of you who don't know, are gates that are digital circuits that that output logic functions such as and, or, nor, and so on. And our design uses essentially elements that have similar functionality to elements that are called resonant tunneling diodes. These are elements that have IV characteristics that look like this. It's basically what you would expect from a diode, except a certain feature has a Gaussian peak with a certain voltage range that actually where current actually decreases when you increase voltage. And under certain biasing conditions, connecting two of these in series can give you digital outputs. And while we don't work with resonant tunneling diodes, we do work with a certain organic molecule that has similar IV characteristics. And I've simulated these using SPICE, which is a circuit simulator. A circuit that I've designed shows simultaneous and or logic. Like I said, these are made of essentially an organic molecule that has adsorption preference to gold. And using self-assembly, I use a monolayer of this molecule for my circuits. And for more information, you can see my poster. Thank you.
Good evening. My name is Yuval Yifat. I'm a PhD student in Kobi Scheuer's Nanophotonics group. Our project, in a nutshell, is in the fabrication and the analysis of nano antenna arrays, as ones that are seen in the SCM micrograph in the upper right side. It has many potential uses, such as detectors, optical sources, and the keystone of the poster, high-efficiency energy conversion, in which we can use it to transfer AC energy from light sources into DC energy, which hopefully will be able to be used for good applications. The measurement setup is quite complicated, and I'll be happy to bore you to death while describing it. And so far, we have pretty good match with between the simulation and the measurement results. Now, the poster may seem to imply that I'm the only one in the group, but I assure you that there are many, many people, and I would be happy to give them credit as credit is due if you will do me the honor of coming to my poster.
My name is Asaf. I work in the group of Gil Markovich, and we are studying the interactions of chiral molecules with semiconductor and metal nanocrystals, and specifically the subject of induced chirality, which the mechanism for is still unclear. And induced chirality in semiconductor quantum dots was introduced just a few years ago, and it was attributed to surface states. It was mentioned there that it's not a phenomena related to the main exciton transitions, and no one really checked the size dependence of this phenomena. And we have managed to show that it's both a size-dependent phenomena and also that we can induce chirality in the main exciton transitions of the dots. We also think that we can derive a scaling law for this phenomena. So if you want to hear how chirality changes with size, I'll be happy to tell you. Also, I've put a picture of this beetle here, which has a pretty remarkable characteristic. This beetle reflects almost entirely left circularly polarized light. And for an inorganic nanocrystal, this is much more surprising since it has a much higher degree of symmetry. And still, I'll try to convince you that we managed to measure these effects in semiconductor quantum dots. In addition, we also introduced some synthetic methods to create hybrid systems of metal nanoparticles and quantum dots, semiconductor quantum dots, in which we study the effects of chiral induction. These systems have a lot of benefits for the studies of this phenomena over molecule and metal nanoparticles. I'll be happy to tell you all about this in my poster. Thank you.
Hi, I'm Philip Schiff, and I'm in the group of Abraham Nitzan in the School of Chemistry at Tel Aviv. The title of my poster is Heating and Thermoelectric Effects in a Molecular Transport Junction with Reorganization. Transport in molecular junctions, whether they're layers or single molecules, is a topic of great interest in recent years. We're interested in understanding not only the current phenomenon, but the heating and thermoelectric effects. We build a simple model based on the Marcus picture of electron transfer to understand heating effects in a hopping regime. We derive the transfer rates and the rates of heating. And we go on to, I'm not sure how I'm going to advance this. Well, and we, okay. So, and from that, we're able to we build a model where we include thermal reservoirs for the leads and one associated with the molecule. We compute the heating effects in all of these reservoirs, calculate the efficiency of the effect, and compute the Seebeck coefficient. One interesting addition that this work provided was an understanding of how the inclusion of reorganization energy affects the heating and thermoelectric effects. So my poster is on the short side here, nestled in the back. So I'm happy to tell you more. Thank you.
Okay, hi everyone, my name is Michal and I'm from Yoram Zeltzer's group. My research deals with single molecule electronics. We are measuring the conductance of amine terminated molecules with the squeezable break junction technique. This technique was introduced over 20 years ago, but yet up until now no one had used it for these kinds of measurements. Okay, so the junction itself consists of two electrodes patterned on 1 millimeter glass. We place a drop of a solution with the desired molecules between the two glasses and then squeeze them against each other, and we expect to trap a molecule in this squeezing and releasing process. We place the sample into the setup itself, and the squeezing force is obtained by phosphor bond leaf, which presses the top electrode, causing it to bend toward the bottom electrode. Based on forces calculation, we found that the stepping resolution is about 1 angstrom, which basically means that upon each step, the top electrode approaches the bottom electrode a distance of 1 angstrom. We also found this calculation to be pretty much precise when measuring the tunneling current in the junction as a function of the distance between the two electrodes. This dependence is known to be exponential, so with just a slightly mathematical work, we could extract the stepping resolution value, and we found it to be 0.9 angstrom, which is pretty much close to the value we calculated. Okay, so the results obtained from these measurements were pretty much satisfying. Here you can see the point contact results with stepwise conductance traces, with steps at the value of the quantum conductance and even twice this value. And the histogram, which is built up from hundreds of these traces, also shows some nice peaks at the 1G0 and the 2G0 value. And the even more exciting results obtained when measuring with molecules. As I said before, no one had used this kind of setup to measure with molecules, the conductance of molecules. And also here you can see the step trend in the conductance trace. Here are the steps at the value lower than the 1G0, which is typical for the measured molecule. And also the histograms show a clear and nice peak at the same value. That's it. Thank you very much. If you're interested in hearing some more, please drop by my poster. Thank you.
Well, I I know I should speak about fullerene-based electronics in this 7th conference of the Center of the Nanoscience. But now I'm going to speak about fullerenes, because I call it the 26th conference for fullerenes. They've been discovered 26 years ago, and since then they are promising, very promising candidates for electronic compounds. Probably think that it's because of the science or the size or something like that, but no, this is because of capitalistic ambitions. Because they want their big and new iPhone or iPad. That's because they want to hear the music of this horrible singer. It's because they want to play with their Xbox, doing imaginary stuff like those things, which they are not even playing. This is their real ambition. While they do that, they don't think about the very basic pain of the fullerene. Fullerenes, because of those reasons, have been jumped from side to side at horrible temperature of 1.5 Kelvin. If you don't believe that, you can check this. More, if you take a look, people have observed them using STM, which is use highly electric field, and it's horrible. And the most horrible thing that you can even think about is the inhumane experiments trying to change them, those beautiful creatures. Because of that, I'm giving you revolution. Revolution of how we think about fullerenes. Because what we really need to think about is the fullerene collective. As a collective. And this is the only way the fullerene will succeed. Now, thank you. You're taking my time, and I don't have plenty of those. Other capitalists will call that self-assembled monolayers. Don't believe them. It's collective, right? Now, as a collective, the fullerenes, we're going to work at room temperature, not at 1.5 Kelvin. We're going to use less voltage on every fullerene. We're going to have those unique fingerprints, and we control on how many of us are going to be employed. This is what we're going to do. We're going to use the collective, right? Now, if you want to know any more about those, go to my poster, or just trust our leaders.
Hi, my name is Gilad, and I'm from Yoram Delzer Group. The subject of my poster is molecular electronics and how to characterize molecular properties using electronic spectroscopy. Okay, I present how we fabricate the molecular junction, a suspended wire junction, and we characterize it using current voltage spectroscopy, which lets us information about the electronic spectrum, and the inelastic electron tunneling spectroscopy, which gives information about the vibrational spectrum of the molecule using electronics. Now I present you a different molecule, the 6-ferrocyanilhexantiol, which you can see in the red curve. There are steps in the function which can be attributed to reduction and oxidation phenomena of the ferrocyan unit. I also present the transition voltage spectroscopy. If we look on the IV curve, there is no much difference between the four different molecules and the ferrocyan. But if we change the axis of the plot, you can see that there are two different slopes of the curve. That one of the linear one is direct tunneling, and the change in the slope is from resonant tunneling of the molecule. You can see in the case of the ferrocyan, there are two different peaks which are in agreement with the conductance spectrum. Also, I present the theoretical explanation and an example, and you're cordially invited to see the poster and discuss about it.
Hi, I'm Michael Ioffe. I work with Fernando Patolsky on drug discovery, drug detection. Now, it is important to detect drugs. Everybody knows why. For forensic needs, for stopping drug smuggling, etc. Lately, a family of a so-called date rape drugs climbed in their use, and the criminal elements use them for sexual abuse and robberies. What they actually do, they either knock you out completely or cause a sense of euphoria or make you sleepy, and while these conditions, everything can be done to you, no physical violence required. And another thing why criminal elements like them is they're flushed out of the body very quickly. So by the time the victim is awake, actually nothing can be proven beyond reasonable doubt, which makes conviction very hard. And they're very hard to discover on spot. You need the special lab equipment for that. Previously, some attempts for making such an on-field, on-spot detector were made in the United States. Forensic specialists, however, regard them as a failure because they, A, make about 30% of false positives, and B, you virtually have to establish a lab in wherever you are, whether it's a rave party, restaurant, pub, whatever. What we have done here is we have developed a method that actually overcomes all the mental difficulties. It's simple, it's cheap, and it's applicable on spot. If you want to know more, please visit me at my poster. It has the same background. That's actually the molecule which was spotted on in this glass of martini or other drink, and it's scared. Or maybe it's some chemist who drowned himself while making that.
Hi, my name is Adar Cohen, and I'm from Ehud Gazit lab. My subject today is nanospheres, stability, rigidity, and function as a new carrier for drug delivery applications. In our lab, we are working with the diphenylalanine peptide. We can form nanotubes, hydrogels, and nanospheres, and I'm working on the nanospheres. The diphenylalanine has in one side of the peptide we have the carboxyl group, and the other side we have the Boc group. It's three materials. And it forms in several conditions spheres. As you can see, the diameter is range from 30 nanometers to 2 microns, and we checked one of our PhD students, post-students. She checked their physical properties, and she saw that their point stiffnesses range from 430 to 800 Newton per meter, and their Young modulus range from 200 to 275 gigapascal, more than strong steel. So in my poster, I'm presenting their stability after lyophilization procedure, and one of my first difficulties was labeling them because they're very sensitive. So I managed labeling them with fluorescein and cleaned the rest of the fluorescein molecules by magnetic beads. If you have any questions, I will be more than happy to answer them. Thank you.
Okay, so the topic of this work is electrical detection of surface plasmon-polar electrons by 1G naught gold quantum point contact. This work was done under the supervision of Dr. Yoram Zetzer. Oh, okay. Okay. So first, metal quantum point contacts are constriction of one or few atoms between two metal electrodes that have a quantized conductance of 1G naught. Formation of this contact is made following our previous procedure by applying a high bias voltage across a small gap between 2 gold electrodes, and until a jump to contact to 1 G naught is achieved, mostly to 1 G naught. So then we take these junctions and illuminate them with laser irradiation, and see that we have enhancement in the conductance that we can calculate it by separating the light off conductance and light on conductance. And we also see that the conductance responds to modulated irradiation of the laser. Okay, here you can see the electrical plasmon detector. The difference is that we illuminate the laser spot in a distance from the junction, and coupling of light to plasmon is induced by a periodic set of regions. So the plasmon can create and propagate it toward the junction and induce an enhancement that in this junction constriction that can be detected by the conductance. So the conductance is reducing with increasing distance of the illumination. And then we can fit a photo-assist transport model that is suitable for this non-monotonic curve, you can see. So for more details, please come to my poster. Thank you.
Good evening. My name is Denis Grozman. I'm a PG student in Ori Chechnovsky lab. So let me break the routine and start from the end. So I invite you to see my poster. Thank you. In this moment, our research is focused on bismuth quantum dots, which are synthesized by Deborah Marchak from Yoram Zeltzer's group. Those particles, except the fact that they are very funny looking, which is a truncated rhombohedron, they have some very interesting properties like, okay, I'll explain it to you personally near the poster. They are highly anisotropical particles. Okay, but if you look at them on TEM, you can see that those particles are constantly rotating under the beam of the TEM. This is very interesting, and we think we have some explanation now. So we decided to check some, excuse me, where's the second? Okay. So we decided to check the electric transport and electrical properties of the particles under the STM system in our lab. Here you can see some spectrums of IT when you're constantly measuring the current, tunneling current of the same particle for some period of time. It's very strange and interesting, and now we have an explanation. I'll say it again, explain to you near the poster. And here we see some very strange behavior of the single particle when the single quantum dot have several different band gaps in one time. But I will explain it to you later. Thank you.
Hello, my name is Erez Tadmor. I'm a master's student at Shimshon Barad's lab. The project I will present now is dealing with nano ferromagnetic rings made of permalloy. The reason to study rings is because they exhibit a vortex state. This is their hysteresis curve. If you know hysteresis curves, they usually have two stable states. You can see this curve of the ring has three stable states. The middle one is a vortex state, and the vortex state is very interesting application-wise because it exhibits a very small stray field and very a little sensitivity to the edge, which is very good in applications such as data storage and sensors. So we study very dense arrays of those rings. And when we study them in dense arrays, we see effects of the arrays on the rings. You can see here in this experiment, we simply rotated our array, and we saw that the hysteresis curve is narrowed. It means that the transition from onion dipole state into the vertex state happens at lower or higher field, depends on the direction you look from. We saw the same thing in the simulation, micromagnetic simulation we made on 3x3 arrays of rings. And here you can see snapshots from the simulation. We see the mechanism of the transition. When in a single ring we see nucleation of small vortices, and in arrays, dense arrays, you can see pinning of the domain walls, and then movement of the less pinned domain walls through the arm of the onion, and transition into vortex. I'll explain the rest near my poster. Thank you.
Okay, so hello, my name is Daniel. I'm from Gil Markovich Group. My poster is focused on ultra-thin conductive and transparent film. Our technique is based on gold, silver, and nanowires. Two routine requirements that we always have from such film is high optical transmission and addition to high electrical conductivity. The new generation of optoelectronics devices like photovoltaic cell and OLED increase the requirement for transparent conductive electrode with new strict need. For example, there must be today flexibility and mass producible. One nice work that has published several months ago by Ujima, he suggests graphene film to do a touch screen. Our technique to prepare ultra-thin metal nanowires for transparent electrode are really cheaper and a simpler way. Our technique leads to high transparency, flexibility of the film, and high electrical conductivity between the device and the ultra-thin nanowires. In the left image, you can see 10 images that indicate for successive ultra-thin nanowires also for macroscopic area. And for more details, you can come to my poster. Thanks.
Good evening. My name is Dina, and I'm a student of Ronit Sachi Fainala. I will present today our work on nanoscaled polymeric carriers for targeted doxorubicin delivery to tumor cells and tumor vasculature. And the formation of new blood vessels from pre-existing vasculature is called angiogenesis. This process is crucial for tumor growth, progression, and metastasis. The newly formed blood vessels are hyperpermeable with disorganized pathology. This, together with poor lymphatic drainage, allow passive accumulation of macromolecules in tumor tissue. Angiogenic vasculature, angiogenic blood vessel express unique molecular markers that are not expressed on normal blood vessels. One of these molecular markers is the alpha V beta 3 integrin, which is an adhesion molecule, and is overexpressed on proliferating vascular endothelial cells, but not on quiescent endothelial cells lining mature vasculature. Alpha V beta 3 integrin is also overexpressed in some tumor cells, which makes it an attractive target for anti-tumor and anti-angiogenic therapies. For the delivery of chemotherapeutic drugs, such as doxorubicin, we developed 3 different delivery systems by using biocompatible and clinically approved polymers. The first system is PLJ nanoparticles formulated to entrap doxorubicin within the inner layer, the inner space. These nanoparticles degrade at acidic environment with the presence of water to lactic and glycolic acid and release doxorubicin in controlled manner. The second system, in the second system, we conjugated doxorubicin with polyethylene glycol by using phenylalanine lysine dipeptide spacer cleaved by lysosomal enzyme cathepsin B. In the third system, we conjugated doxorubicin with polyethylene glycol by using acid-liable hydrazone linker, and this system was chosen to further conjugate it with targeting moiety, the bicyclic RGD peptide, which is specifically targeted the alpha V beta 3 integrin. The pegylated doxorubicin bearing the RGD peptide inhibited the adhesion of human umbilical vein endothelial cells to the fibrinogen as opposed to controls. It also decreased the viability of FUVEC in a similar manner as free doxorubicin and the not targeted conjugates. To study the in vivo distribution of our targeted conjugate, we coupled it with near-infrared fluorophore. This compound was preferentially accumulated in tumor sites rather than in other selected organs. It also showed 15-fold accumulation as opposed to non-targeted compounds. To hear more, I would like to see you at my poster and enjoy this conference.
Okay, let's thank again all the flash session speakers for keeping time. So we're back to schedule. Dining hall is actually open from 7 for dinner. At 8:30 we have beers, hot drinks, and snacks, and exciting poster session. Tomorrow morning session starts at 9. Speakers, please come a few minutes earlier to make sure your presentation shows correctly.